Hello, we have been discussing the determination of stiffness and strength parameters using micromechanics models, and we understood in last few lectures the determination of the stiffnesses as well as the strength parameters like of a composite using micromechanics model, especially with mechanics of material approach, and we also understood some of the limitations of those approaches, and today we will discuss the determination of coefficient of thermal expansion and coefficient of moisture expansion, basically the parameters which are responsible for hygrothermal response of a lamina. We understood already in one of the previous lectures while discussing the hygrothermal stresses the importance of the hygrothermal determination of hygrothermal stresses, and in order to determine the hygrothermal stresses in a laminate we must know the hygrothermal responses of a lamina, and in order to understand the hygrothermal response of a lamina, coefficient of thermal expansion and coefficient of moisture expansions must be known. So, again in order to determine the coefficient of thermal expansions, I mean there are some micromechanics model, and today we will discuss how to determine the coefficient of thermal expansion. Okay. So, as we know that for a lamina, because it is orthotropic, so coefficient of thermal expansion is also direction dependent. So, with reference to the material axis, where suppose if we consider this lamina where 1 toward the principal material axis, 1 is the longitudinal axis and 2 is the transverse axis, there will be coefficient of thermal expansion along longitudinal direction and coefficient of thermal expansion along the transverse direction will be different. Generally, the coefficient of thermal expansion of this fiber reinforced polymer matrix lamina in the longitudinal direction is much less compared to that in the transverse direction. The reason is in the longitudinal direction the fiber is having a coefficient of thermal expansion which is much lower than that of the matrix, and it puts restraint on the expansion in the longitudinal direction. So, suppose we consider an RV like what we have done earlier also, representative volume element where this is the fiber and others matrix. Okay. So, suppose alpha 1 is the coefficient of thermal expansion in direction 1 and alpha 2 is the coefficient of thermal expansion in direction 2, and alpha f and alpha m are the coefficient of thermal expansion of the fiber and the matrix respectively. So, first let us see the determination of longitudinal coefficient of thermal expansion, that is alpha 1. Okay. Suppose we consider the same RV with all those assumptions which you have discussed also hold good here, like perfect bonding, uniform fiber spacing, all these assumptions are true here also. Suppose this composite is actually experiencing a temperature change of delta T. Okay. So, when it experiences a temperature change of delta T, there is no mechanical load applied. Okay. It is only experiencing a temperature change of delta T and no mechanical load. Recall how we have actually established the relationship for longitudinal Young's modulus of a lamina. So, if F 1, suppose F c or F 1 is the force in the composite along direction 1, this is actually shared by the fiber, F f is the force in the fiber, F m is the force in the matrix. But in this case, because the composite is not subjected to any mechanical load, therefore, there is no net load applied in direction 1. Okay. So, however, even though there is no net load applied, there will be stresses induced in the fiber and the matrix, okay, because of the mismatch of coefficient of thermal expansions. Okay. Because alpha f is not equal to alpha m, that leads to stresses in the fiber and in the matrix. I think we have discussed these things in details. Stress in the fiber and sigma m is that in the matrix. The reason we have already discussed in while studying the hygrothermal stresses, because this is perfectly bonded, therefore, under this delta T they will have same longitudinal expansion, okay, maybe delta, okay, and therefore, they will also have the same strain in along direction 1. Okay. But suppose the fiber and the matrix are actually unrestrained, okay, they are free, then the expansion of the fiber and the expansion of the matrix would have been different. Therefore, some amount of expansion is actually some amount of strain actually restrained, and that leads to the development of stresses. Okay. So, we can write this, since the net force is 0, F 1 is equal to, actually we can write the stress in composite, actually there is no net stress in the composite, sigma c sigma into AC, AC is the area of the composite, is equal to sigma F A F. With respect to this, with reference to this, the representative volume element which we have considered, we can write is equal to 0. Okay. Therefore, we can write that sigma c is equal to sigma f V f plus sigma m V m is equal to 0. This is equation number 1. I think we know with reference to this R V that actually the ratio of the cross sectional area of the fiber to that of the composite is the representative volume, I mean the volume fraction of the fiber. Similarly, A m by A c represents the volume fraction of the matrix, because they are having the same length. Okay. Okay. Now, what is this sigma f? Even though the net force is 0, there will be stress in the fiber, there will be stress in the matrix, but the stresses are induced in such a way that the net force is 0. Now, let us try to understand what is this stress. So, suppose epsilon 1 is the strain of the composite, strain along 1. Okay. Now, if the fibers are free, then the strain in the fiber would have been free strain in fiber would have been how much? Alpha f into delta t. Similarly, free strain in the matrix would have been alpha m into delta t, but then they are not allowed to expand freely because they are restrained, because the perfect bonding between the fiber and the matrix. So, the amount of restraint in the fiber is epsilon 1 minus alpha f into delta t. Okay. This is the amount of restraint in the fiber. Okay. Ideally, it would have expanded by alpha f into delta t, but now it is allowed to expand only by epsilon 1. Okay. So, multiply this by the Young's modulus of the fiber will actually give us the stress induced in the fiber. Okay. Similarly, the stress induced in the matrix is sigma m is Young's modulus of the matrix E m into epsilon 1 minus alpha m into delta t. Okay. If we put this 2 and 3 in 1, therefore, 1, 2 and 3 gives us, we can put this value of, put the expression for sigma f here, therefore, E f epsilon 1 alpha f delta t, this is sigma f into V f plus E m epsilon 1 minus alpha m into delta t into V m is equal to 0. Okay. So, we can now take the terms containing epsilon 1, therefore, we write E f V f plus E m V m into epsilon 1 is equal to E f alpha f V f plus E m alpha m V m whole thing into delta t. Okay. So, I will write it again. So, what we got is that epsilon 1 into E f V f plus E m V m is equal to E f V f alpha f plus E m V m alpha m into delta t. Therefore, epsilon 1 is equal to E f V f alpha f plus E m V m alpha m divided by E f V f plus E m V m. Okay. Now, this is the equation number 4. Okay. Now, how we define the coefficient of thermal expansion alpha 1? Alpha 1 is the coefficient of thermal expansion of the composite, okay, of the composite along 1. Therefore, if the composite experiences a temperature change of delta T, then because of this delta T, the strain along 1, the longitudinal strain along 1 is nothing but alpha 1 into delta T. Now, if we compare 4 and 5, if you compare 4 and 5, that gives us alpha 1 is equal to E f V f alpha f plus E m V m alpha m divided by E f V f plus E m V m. Okay. So, basically this is the longitudinal coefficient of thermal expansion. Now, you may take note of this. What is this? E f V f plus E m V m by the rule of mixture is nothing but longitudinal Young's modulus of the composite. Okay. We have already seen that while determination of longitudinal Young's modulus of composite using mechanics of material approach. Therefore, we can write alpha 1 is equal to E f alpha f V f plus E m alpha m P m by E 1. Okay. So, this is what we get. Okay. So, this is what is, say, this is the equation number 7. Okay. This is the expression for longitudinal coefficient of thermal expansion for the composite. Now, you can see that this is actually of the form that like this E 1 is equal to E f V f plus E m V m. Similarly, here also this is this into V f plus this into V m, but it is not alpha f V f, alpha f E f by E 1 and alpha m E m by E 1 to V m. So, this is the longitudinal coefficient of thermal expansion in terms of E f E m and V f V m, and of course, as a function of the coefficient of thermal expansion of the fiber and the matrix. Okay. Next, let us see the determination of transverse coefficient of thermal expansion. Now, here also we take the same representative volume element. Okay. subjected to delta t and no mechanical load, okay, no only subjected to delta t, okay, no mechanical load. Now, already we have seen in our previous discussion that when this representative volume element, when the composite actually experiences a temperature change of delta t, what happens in the direction 1? Suppose the strain in this direction is a epsilon 1 because of the perfect bonding, fiber matrix and the composite experiences the same strain along 1, suppose it is epsilon 1. Therefore, the restraint for the fiber is this much, the free expansion of the fiber would have been alpha f into delta t, we have just now discussed. Similarly, the free expansion of the fiber would have been alpha m into delta t. Therefore, this is the restraint for the fiber, restraint for the matrix, and this induces the stresses in the fiber along direction 1 epsilon sigma f 1 is equal to this, say this is equation number 1, and the stress induced in the matrix along direction 1 is given by this, say this is 2. Note that these are the stresses induced in the fibers and the matrix. However, the net load along the net force along the direction 1 is 0, that we have discussed already. Okay. So, now what are the strains? What happens to, we will now see because of this what happens in the direction 2, because we are trying to determine that coefficient of the thermal expansion along direction 2. So, in the direction 2 the strain is for the fiber is alpha f into delta t, okay, plus there is Poisson's effect. Okay. What is this Poisson's effect? If nu f is the coefficient of nu f is the Poisson's ratio of the fiber, and nu m is that for the matrix. Okay. Therefore, because of the longitudinal stress along direction 1, because of this longitudinal stress along direction 1, the strain in the transverse direction is nothing but how you define the Poisson's ratio, that is nu f is equal to epsilon f in the direction 2 divided by epsilon f in direction 1, okay, when only load is applied along direction 1. Okay. Now, in this case, therefore, epsilon f 2 is nothing but nu f into epsilon f 1. Okay. This epsilon f 1 is nothing but sigma f 1 by E f. Therefore, this is the transverse strain in the fiber. Okay. We can use this 1 in this expression and we get this. So, suppose this is equation number 3. Similarly, we use the expression for sigma m from here and we get the transverse strain in the matrix like this. Okay. So, this is the transverse strain in the fiber and the matrix, that means along direction 2. Now, we know if total transverse deformation is delta c, this must be equal to delta f plus delta m. Okay. Now, in terms of this suppose this is actually T f and this is say T m by 2, just recall the same, let me write it here. This thickness is of the matrix is total thickness is T m for the matrix and the fiber thickness is T f. Okay. This gives us that in the transverse direction, okay, epsilon 2 in the composite into T c is nothing but the transverse deformation. Okay. This must be is equal to epsilon f of the fiber, of course, in the direction 2 into T f plus epsilon m in the direction 2 into T m. Therefore, dividing both sides by T c, epsilon 2 is equal to epsilon f 2 V f plus epsilon m 2 V m, taking note of the fact that for this R v T f by T c is equal to V f and T m by T c is equal to V m. Okay. So, we get this. So, we could express the transverse strain in direction 2 in terms of the transverse strain in the fiber and transverse strain in the matrix. Okay. Now, we can put here in equation 5 the expressions for transverse strain from equation 3 and 4. Okay. So, we get epsilon f 2 from equation 3. So, this is nothing but alpha f delta t minus nu f epsilon 1 minus alpha f delta t. So, this is the epsilon f 2, okay, and multiplied this by V f. Similarly, we put the epsilon m 2 from equation number 4, that is nothing but alpha m delta t minus nu m epsilon 1 minus alpha m delta t into V m. Okay. This is the expression for epsilon 2. Okay. What is epsilon 1? We have just seen epsilon 1 is the strain along direction 1 for the composite when it experiences delta t. Therefore, this is nothing but alpha 1 into delta t, where this is the equation number 6, where alpha 1 is the longitudinal coefficient of thermal expansion of the composite. Okay. Therefore, using 6 and 7, we can write epsilon 2 is equal to alpha f delta t minus nu f into alpha 1 minus alpha f into delta t into V f plus alpha m delta t minus nu m, putting epsilon 1 is equal to alpha 1 minus alpha m, sorry, epsilon 1 is equal to alpha 1 into delta t. Therefore, this is alpha 1 minus alpha m delta t V m. Okay. When we combine these terms, taking delta t, we can write here as alpha f minus nu f alpha 1 minus nu f alpha f into V f, okay, into V f into delta t, okay, plus alpha m minus nu m alpha 1 plus nu m alpha m into delta t into V m. Now, take note of the fact that mu f alpha f plus mu m alpha m. So, this is say equation number 8, and taking note of the fact that nu 1 2 is equal to nu f alpha f plus nu m alpha m, and if we combine this, what we get is this epsilon 2 is equal to 1 plus nu f alpha f V f plus 1 plus nu m alpha m V m, okay, minus alpha 1 into nu 1 2 whole thing multiplied by delta t. Now, this is equation number 9. Therefore, now what is epsilon 2? Epsilon 2 is a strain in the direction 2 when this composite experiences a change in temperature of delta t. Okay. Therefore, if the composite experiences a change in temperature delta t, what will be the strain along direction 2 is decided by its coefficient of thermal expansion in direction 2. Therefore, epsilon 2 is equal to alpha 2 into delta t. Therefore, 9 and 10 tells us 9 and 10 tells us that what is alpha 2. This is nothing but alpha 2. So, alpha 2 is equal to 1 plus nu f alpha f phi f plus 1 plus nu m alpha m phi m minus alpha 1 nu 1 2. So, this is what we get. Now, in deriving these expressions, actually the both fiber and the matrix is of course isotropic, is considered to be, that means the properties are isotropic for the fiber and the matrix. There are works where the properties of the fiber has been actually taken considered as orthotropic, and the expression for alpha 2 is obtained. This is actually done by Hassin in 1979 in Journal of Applied Mechanics. Okay. So, this is the expressions for transverse coefficient of thermal expansion in terms of the coefficient of thermal expansion of the fiber and the matrix, and considering orthotropic fiber properties. Matrix is of course isotropic. Okay. Now, you will see that alpha 1 and alpha 2 actually depends on the alpha f, alpha m and their volume fraction, and as I have already mentioned, for most of these polymer matrix composites, fiber reinforced polymer matrix composites, alpha 1 is less compared to that of alpha 2, and that is because in the longitudinal direction the fiber actually restrains the expansion, and therefore, the alpha 1 is less, but in the transverse direction it is dominated by the matrix, and therefore, alpha 2 is more compared to that of alpha 1. We have also discussed in the hygrothermal stress analysis the importance of determination of hygroscopic stresses. Basically, when it is a polymer matrix composite, okay, the matrix absorbs moisture and therefore, it experiences strain, and that actually leads to and because the fiber is almost insensitive to, most of the fibers actually inorganic fibers are insensitive to moistures, therefore, there will be residual stresses, and these residual stresses should be taken into account while analyzing or while designing the components made of these fiber reinforced laminated composites. Okay. So, let us see how we determine the coefficient of moisture expansion. Similar to the coefficient of thermal expansion, the coefficient of moisture expansion in composites are also direction dependent. In the longitudinal direction and in the transverse direction they are different, and because again the difference of properties of the fiber and the matrix. And so, let us see how to determine the coefficient of moisture expansion. Suppose beta 1 is the coefficient of moisture expansion along longitudinal direction, and beta 2 is that for that in the transverse direction, and beta f and beta m are the coefficient of moisture expansions for the fiber and the matrix. And I think we have defined the beta the coefficient of moisture expansion, and it depends upon the moisture concentration. So, delta C c, delta C f and delta C m are the moisture concentration in composite, fiber and matrix respectively. Okay. This is kg per kg. So, what is the strain in the because of the moisture concentration is decided by what is the moisture concentration of the composite or the fiber or the matrix. Please follow the definition of coefficient of moisture expansion. Okay. Suppose epsilon 1 is the strain along direction 1. Okay. Therefore, the stress in the fiber analogous to what we have discussed in the case of thermal expansion. Suppose this actually experiences a moisture concentration of delta C c, that means the moisture absorption per unit mass of the composite. Okay. Now, this delta C c will be actually shared by the fiber and the matrix. So, suppose delta C f is the moisture concentration of the fiber, delta C m is that of the matrix. Okay. Now, given a free expansion, suppose the fiber is given a free expansion. In that case, free expansion of fiber is beta f into delta C f, where delta C f is the moisture concentration per unit mass, okay, of the fiber, and beta f is the coefficient of moisture expansion. Similarly, the free expansion of the matrix is beta m into delta C m. Okay. But then because of the perfect bonding, here also no load, no applied load, okay, only moisture absorption. Okay. So, now because of the perfect bonding, this is the fiber, this is the matrix. Because the perfect bonding, the strain along direction 1 is same for the fiber and the matrix. Okay. So, ideally the strain would have been this is not expansion, actually fiber strain. Okay. Ideally the strain would have been this, if it is free the strain would have been this, similarly the strain in the matrix would have been this, but because they are constrained, therefore the strain is epsilon 1, therefore the difference in strain is given by this, and that multiplied by the Young's modulus of the fiber gives the stress induced in the fiber. Okay. Similarly, the stress induced in the matrix is given by this. Okay. So, now because there is no load, we have already seen that F 1 is equal to F f plus F m is equal to 0, and that, let this be equation number 1, let this be equation number 2, and this we have done it number of times. This gives us sigma f V f plus sigma m V m is equal to 0. Okay. Okay. Now, we can put this expression for sigma f, say this is our equation number 3, therefore 1, 2 and 3 gives us, we put sigma f is equal to E f into epsilon 1 minus beta f delta C f V f plus E m epsilon 1 minus beta m delta C m V m is equal to 0. Okay. Therefore, we can write E f V f, we write the coefficient of epsilon 1 first, E m V m epsilon 1 is equal to E f beta f delta C f V f plus E m beta m delta C m V m. Okay. Therefore, we can write epsilon 1 is equal to E f beta f delta C f V f plus E m beta m delta C m V m divided by E f V f plus E m V m. Okay. So, this could be written as E f beta f delta C f V f plus E m beta m delta C m V m divided by E 1. So, this is the expression for strain along direction 1. Suppose this is our equation number 4. Okay. Now, we can write this as, so let me write this as, so this is this could be written as E f beta f delta C f V f plus E m beta m delta C m V m divided by U 1 delta C C and multiply the whole thing by delta C C. Okay. So, this is equation number 5. Now, going by the definition of beta 1, suppose when these experiences delta C C, the strain along 1 is epsilon 1, that means epsilon 1 is equal to, if beta 1 is the coefficient of moisture expansion of the composite along 1 is in delta C C. Suppose this is our equation number 6. Okay. Therefore, comparing 5 and 6 gives us beta 1 is equal to, so we get this is as the beta 1. Comparing 5 and 6, we get the expression for beta 1 as this. Okay. So, what we could see is that in the expression for coefficient of moisture expansion, we also have delta C f and delta C m and delta C c. Okay. So, we must know what is the moisture absorption of the fiber and the moisture absorption of the matrix when the total moisture absorption is delta C c. Okay. So, equating the total mass, if delta C c into W c, W c is the mass of the composite, okay. W c is the mass of the composite. So, this is the total moisture absorption, and when W f is the mass of the fiber and W m is the mass of the matrix, then the moisture absorbed by the fiber is this much and moisture absorbed by the matrix is this much. So, equating this, we get this relation. Okay. What is W f? W f is nothing but the W f is the mass fraction, mass of the fiber to mass of the composite, mass fraction or weight fraction. Similarly, W m is capital small w m by small w c, mass of the matrix to mass of the composite. So, this is the relation we get, say this is equation number this is equation number 8. Okay. So, now we can write this beta 1 in terms of mass fraction and the volume fraction as well as the moisture concentration of the fiber and the matrix. Okay. So, now converting the mass fraction to volume fraction using density, we have already understood this relation. We can convert the mass fraction to volume fraction using the densities. So, writing this, we can write the expressions for coefficient of moisture expansion in direction 1 as this. Okay. Even here also now we have the expression for coefficient of moisture expansion in terms of delta C f, delta C m. Okay. So, we must know this, but what happens is that this delta C f and delta C m, generally delta C f is almost 0 for most of the inorganic fibers. Okay. They are insensitive to moisture and therefore, this could be neglected. So, similarly we can also determine the coefficient of moisture expansion in direction 2 analogous to what we have done for alpha 2, that means the coefficient of thermal expansion in the transverse direction. In the same way, we can also obtain the coefficient of moisture expansion in direction 2. Even here also the expression contains delta C f and delta C m. Okay. So, in addition to the properties of the fibers and the matrix and the relative volume fraction, we must also know this delta C m and delta C f. However, in most of the polymer matrix composites, delta C f is 0, and hence if you just go back to equation number 9 and 10, if you put delta C f is equal to 0, So, beta 1 becomes this, okay, and beta 2 becomes this, okay, putting delta Cf is equal to 0 in 9 and 10. Also, for composites like graphite epoxy, actually the fiber modulus is far higher compared to that of the matrix, okay, matrix modulus, and as a result of this, in most of these cases Em by E1, E1 is fiber dominated, which is equal to E1 is nothing but EF Vf plus Em Vm, okay. So, this is far higher compared to Em and almost it tends to 0. Therefore, what happens is if you put that, we get that the coefficient of moisture expansion in the longitudinal direction is almost 0, and if beta 1 is put 0 here, then the coefficient of moisture expansion in the direction 2 beta 2 becomes this, okay. So, this is much more simplified here, these terms do not contain delta C f and delta C m, okay. So, this is the expressions for coefficient of moisture expansion in the longitudinal as well as in the transverse direction. So, I will stop here today, thank you.